All right, welcome back to another installment of Violent Earth. All right, it's been a week or so, well, 2 weeks since I made the last video, which was Deep Freeze. So hopefully you just got done taking a look at that incredible event. And now we wanted to, I wanted to kind of roll back a little bit to give a little bit more context on the Earth functioning normally, or just sort of this business as usual context. So then that way we understand that these punctuated catastrophes, or the violent things, are exceptional, right? That they are, they're events that don't happen all that often, but when they do, of course, they impact many of the Earth's systems very violently, right? So in an attempt to kind of roll that back a little bit, today's material, or week 4's material, starts out just a little bit of discussing what I like to call our quiescent crust, or the development of the outer skin of the Earth, the crust of the Earth. That really, you know, the whole Earth is silicate based, but the really light silicate material that occupies the upper 10-40 kilometers that we typically call the crust of the Earth, or a portion of the lithosphere, if you refer back to week 1. Then from the quiescent crust, I'll move on to what we might term violent volcanism, and really just to kind of, not really a spoiler here, but just to throw this out there that we're going to talk about super volcanoes, or really intense violent volcanism, later in the course, where this type of violence that I'm talking about here, this violent volcanism, this is Earth business as usual, but to the human scale, this is really violent. Okay, these are violent events where people do lose their lives, lose homes, lose property, so on and so forth. Okay, so we'll take an adventure into violent volcanism, which is a big part of this process of making the Earth's crust. Okay, and then from that, I want to then talk about global tectonics. We, to this point, I have not invoked the larger theory of plate tectonics, which is kind of this all-encompassing theory of the Earth and how the Earth functions. And I want to do a little bit of that today. So we're going to kind of dance around between all these topics over the course of this next lecture, which I'll try to break up into some segments so we don't have you know, a really long 3-hour continuous video again, but we'll see how that goes. All right, so first of all, let's talk a little bit about the making of crust. This is what's known as the ophiolite sequence. This is just a drawing of this, my own drawing, that I like to do in class. And we'll go through different portions of that during the beginning of this lecture, this topic. Then we'll transfer to a topic called, or a process called subduction. And here, this ophiolite sequence, I've minimized those and put these little pictures of the ophiolite sequence over here to represent the oceanic crust, which is made of this ophiolite sequence, this sequence of rocks that form from one another. And that is the main material that is undergoing this subduction process in the process of subduction, or what ultimately causes arc volcanism, or a volcanic arc, just like the Cascade volcanic arc. Okay, so we'll do making oceanic crust, then the process of subduction, which arguably is really the process of making, instead of oceanic crust, making continental crust. Then I want to take a few minutes to really just talk specifically about volcanism. And here's Mount St. Helens. Of course, after the dome blowing event of 1980, I think this is a 1984 picture with the small dome that has reformed in the middle. All right, now to recap where we've sort of been, our spiral is slowly getting larger. Our spiral is slowly getting more detailed events as we go. So we started off with a little bit of cosmology, the cosmic web, and the idea of fractals, then to scale a lot more towards our scale, or at least to the scale we can kind of think in a little bit better, which is, instead of the cosmic scale, the solar system scale. And the making of a solar system on this accretionary disk, and the small planetesimals and protoplanets that then ultimately became the planets that we know and love, including Sedna and Pluto. Then we briefly touched the thermonuclear generator of the sun that creates all of the light and warmth that we interact with here on this planet. Of course, important for life on Earth as photosynthesis. Then in that first week still, also touched on the layering of Earth, and more so rather than going just through the layers to try to teach these individual layers and what these are and putting a name with each of those, I really focused a lot more on how do we know this stuff? What's the process behind our learning on how we know that the Earth is layered? Then the first big event that we really discussed is known as the Big Impact Hypothesis. This is the planetesimal size Theia that impacted with the planet Earth to create from the ejecta of that impact the moon. Then we continued to really focus on the heliosphere here, or the whole solar system, and we looked through orbital cycles and how the individual orbits, or the orbit of the planet Earth, and asymmetries in that orbit have an effect on the global climate. And then that launched us into this heliospheric perspective, launched us into a conversation about climate and climate change here on Earth, which inevitably led us into talking about glaciation. And first of all, the Pleistocene glaciation, or which oftentimes is referred to as the Ice Age, right? In common media, I would say, or like the recent children's cartoon, Ice Age. And then so we couldn't move on from the Ice Age or the Pleistocene Ice Age event without talking about megafaunal beasts, things like mammoths and mastodons, in here the Titanus, though we only touched on that for a minute. Then from the Pleistocene, we then jumped to a much older glacial period, the Neoproterozoic glaciation, about 700 million years ago. In this event, collectively called the Snowball Earth hypothesis, the Snowball Earth. Now, to finish out that spiral today, we're going to do a little bit of baking the Earth's crust. So here you have some continental crust, some oceanic crust that's being subducted, some oceanic crust that's undergoing divergence, crustal divergence, and then a different style of subduction zone over here where oceanic crust is subducting beneath oceanic crust. Okay? And then what's really important to focus on in this diagram, sometimes we blow this up and we focus on the grand scale of things, but then forget the daily manifestation of this process is this stuff, is volcanism. And every day there are volcanoes that are erupting around the Earth somewhere. There is some amount of molten material that has undergone this process, or one of these processes of melting, to form molten magma that's then being expelled into the atmosphere of the Earth, which we call volcanism. Okay, so that's our spiral for today, to kind of recap what we've gone over in the last 3 weeks. Now, one thing that I have not addressed since the very first week is the calendar of this class, or what I like to call the geologic time of this class. So taking all of our big catastrophic events that are focused on in this class, in Violent Earth, and then placing each of those events on a 10-week calendar. So here at Treasure Valley Community College, or in the whole Oregon university system, we use 10-week terms. So fall term, winter term, spring term, and then summer term, or quarters is another way to think of that. And they're 10 weeks each. So because of that, I've reduced the entire scale of geologic time, 4.5 billion years of Earth history, 4.6 billion years, or another way to think of that, 4,600 million years, and we've reduced that into 10 weeks, or 7 days a week, into 70 days overall. Now, this was addressed in week 1, but I haven't come back to this because we haven't really gone through enough events to place our events on the calendar. Now that we have, I wanted to take a minute to show you how to calculate these for the upcoming exam, which next week, week 5, there'll be new material revealed at the beginning of the week on impacts or extraterrestrial impacts, meteor impacts, asteroid impacts, and then an exam if you were registered for this class. So to calculate these where to put your event on this time scale, each day roughly is about 65 million years per day to get up to a total of 4,600 million years. So the best way or easiest way to calculate this is to take the event that's in question in its respective number of millions of years, and then divide that by 65 million years per day. So your millions of years cancels out and you end up calculating days. And then you take that number of days and count backwards from today to get to your number. So for instance, if we want the giant impact hypothesis here, that happened 4.48 billion years ago, or to expand that into a million-year nomenclature, 4,480 million years, divided by 65 million years per day. Millions cancels out, we're left over with days. That would be 68.9 days ago from today, which of course, at 70 days in the calendar, 68.9 is a day and a half into the term. So effectively putting the giant impact hypothesis at the very beginning of our overall timeline. Okay? So please, if you're registered for the class and you're worried about this calculation at all, please email with any questions, or there's other ways to reach out to me if you're not registered for the class. But I hope this makes sense, and I don't want to get bogged down in any of the math. This is simply a means to take all the really cool, violent, catastrophic events that we're talking about in this class and to put them all on one diagram that's basically representative of geologic time. Another way to do this, as was discussed in the first week, is we could maybe do a 24-hour clock, right? And we could place the events on a 24-hour clock. Or another great way, and I think I've posted this on the Canvas website, is the length of an arm. If we take 4.6 billion years here and go the length of a human arm all the way to the end, we could also place events along here. Okay, so that's a good, more like a bar type of scenario, right? Like you're hanging out at the bar with your friends, or maybe waiting in the grocery line at the store, and you could tell somebody the story using your arm. But in this case, I wanted to, for the class, expand that out a little bit into context of our class. Now, one thing I want to point out is that this is not a syllabus, right? This is not order of events as we've discussed them through class, okay? The Pleistocene glaciation, arguably that is still occurring today, but last glacial maximum about 11,700 years ago, but starting 2.5 million years ago, that's effectively going on today on our calendar, right? So similarly, you could do this whole calculation and you find that this is in the last minutes of day 70. Now, I point that out now because we talked about Pleistocene glaciation during week 3. If this was a syllabus, this would go up here, but that's not what this is, right? This is a graphical representation of where to put our big violent events on the calendar, okay? So here we have origins of the solar system, 4.6 billion years ago. Giant impact hypothesis, 4.48 billion years ago. Then we fast forward a long ways of geologic time where we haven't talked about anything. We haven't addressed any of this stuff, all the way to about 700 million years ago to the snowball Earth event, and then relatively recently to the Pleistocene glaciation event. Okay? Now that's all of the big things that we've talked about so far. After today, we will have a few more things to place on this calendar, which we'll do during the lecture. Next week, we have a few impacts that occurred at different times in geologic time that we'll be able to place on here too. For instance, 65 million years ago, the dinosaur killing asteroid, that happened 65 million years ago. If every day represents 65 million years, then that happened right here between day 69 and day 70. Okay, so we'll be able to place that there. All right, moving on then. Today, what we're going to do is place the making of oceanic crust, the making of continental crust, and the idea of cratons, or stable pieces of crust that have been long existing. They're billions of years old, and they're also not very deformed on the interior of these cratons. So this is an example of the North American craton. Here, all these colorful portions here would make up the North American craton. So we'll get more into this and be able to place those on the map. Okay. All right, need to reel back a little bit and get into information mode here. The image here is going back to the idea of a layered Earth, right? This is sort of where we started out with some of these fundamentals, so this is a good place to pick up again with these fundamentals as we lead towards the theory of plate tectonics. So shown here on one side is the compositional layers, crust, mantle, core, and then the mechanical layers, which have these very physical differences rather than compositional or chemical differences. Lithosphere, asthenosphere, mesosphere, outer core, inner core. And remember, they all have different properties to them. So for instance, the inner core is solid, metallic iron and nickel, while the outer core is liquid, metallic iron and nickel. So these have different physical characteristics with them. Now, superimposed on top of this, what I'm saying here is that these layers also, because of their physical and chemical differences, they're manifesting different gradient properties. Okay, I know that's a little bit heavy or wordy to say, but let's just look at the arrows right here. On the chemical side, on the compositional layering side, one way to think about this through chemistry is that the lighter material floats towards the top. Right? Where the heaviest material is sunk towards the center of gravity, towards the center of the Earth. That's the core. Well, as we're talking about making crust, making the Earth's crust, another way to think about this, I like to think about it this way anyway, is the lightest stuff of the Earth, the lightest compositions, are floating up towards the surface continually. Okay, so that's what we're going to get to today, is how this crust of the Earth has slowly thickened over time. Okay, we didn't start out, the Earth didn't start out with a crust that's 40 kilometers thick, like in some areas of the interior of the cratons of Earth today, like say underneath the Himalayan mountain range, 40, 55 kilometers thick. That didn't happen overnight, so we want to look at the development of how this chemistry has changed and how that has affected the second side, the physical side of, instead of there being gradients of chemistry, gradients of heat. Okay, so as the interior of the Earth, remember the primordial heat is trapped within the Earth because silicate rocks and minerals are poor conductors of heat and electricity. Thank you, Paul Wallace. Poor conductors of heat and electricity. Heat doesn't transfer through the rocks very easily, right? If I take this piece of granite and I heat it up in a fire on one side, right, and it starts to get warm, it's going to take a long time before the other side of this rock gets warm enough that I'll feel it or it'll burn me. Where, on the other hand, if I was to do this with a piece of metal, right, I put a piece of like a metal rod or a branding iron into a fire, say that long, heats up that side, the heat is going to easily travel on those metallic bonds to the other side of the wire or whatever it is. Metals are conductors of heat and electricity, where rocks, they're mostly silicates or the same composition of glass, right? Like a glass window or a glass insulator on top of a power line, right? Those are, or porcelain, those are good insulators against heat transfer and electricity. So what I'm getting at here is rocks being poor conductors of heat and electricity. The Earth, even though this heat, this kinetic energy was generated 4.5 billion years ago, the Earth still retains that heat on the interior. It's still hot down there, right? It's not cooled off. That's what's keeping this stuff molten, the molten outer core. Now, that said, just out there on the other side of the crust is the cold vacuum of space. It's cold, it's freezing cold out there. There's almost the absolute absence of temperature, right? There's nothing. It's the cold vacuum of space. At that interface is where we live. At the crust, couple kilometers up, cold vacuum of space. And it's the atmosphere, then, that retains some of that heat. But it's not the Earth's heat that the atmosphere retains. Remember, that's sunlight that's coming in that warms the atmosphere. All right? All I'm pointing out here is that the Earth is hot in the interior, and that's being slowly released out of the Earth's crust into the cold vacuum of space. Okay? Now that then, along with the chemistry floating, have an impact on the development of crust. Okay? Early on, when the Earth had very little crust, this was able to go right out, right? There's nothing, there's no insulator. There's no insulator there, there's no hot pad. If you get some something hot out of the oven, right? You use a hot pad. Early on in Earth, where there was no crust, there was no hot pad. So the hot stuff was able to leak out into the cold vacuum of space probably quite readily, leading to a faster cooling off. Now through time, which is what we'll focus on here, as the crust has developed a thicker mat of insulator, and this heat then must be escaping more slowly. Okay? All right, so takeaway here from this slide is to focus on the mechanical and physical layers, as we've talked about before, but now to kind of see them in a slightly different pattern as heat escaping from the into the Earth and the chemistry, the lighter stuff, floating. And not to draw any really major anthropomorphic analogies here, but maybe you've been looking at the side image over here of the skeletal system, the lymphatic system, the nervous system, the muscular system. The human body, or all organisms, we also have this kind of layering as well, that also manifest biologically for us in different ways. And now I'm not trying to anthropomorphize the Earth and to make this too much, but I am drawing this just simple kind of fun analogy that you can think of it this way, as the Earth has an internal structure, just like we do, because we have a function. Now, the Earth doesn't just have an internal structure for no reason. There's a function behind that internal structure, right? So chemistry being the function here, and the escape of heat being the function here. Okay, so this is a paper, excuse me, I don't think I have the reference down here, but this is referencing two different diagrams. This is a paper from a few years ago focusing on the development of the Archean crust, or the development of oceanic crust through time. And the first image here is the Hadean time period. All three of these are within the Precambrian, as we've defined in this class, the earliest segment of geologic time, Precambrian, from 4.6 billion to 542 million. All of this is during that time. Okay? The Proterozoic, the most recent 2.5 million to 500 million of that time. The Archean and Hadean, then older than that. The Hadean, this is like, look at the name, right? Hadean, Hades, or the ruler of hell, right? Hell on earth, or the hell period of earth, the hell times. The Hadean time period is not a great time for life, right? Or if you're thinking about life, then there's nothing living at this time. This is also, there's meteors still that are bombarding the earth. There's probably immense volcanism as the outgassing of the carbon dioxide and water vapor from The interior of the Earth is violently coming out. This is a time of hell on Earth, or probably the most extreme violence that you can imagine. Maybe an analogy, a planetary analogy, what this is similar could be, maybe Venus, as well as we can think of Venus with a very hot atmosphere. Now the compositions of the atmosphere are not directly analogous, but just think of a hell planet. Okay, during the Hadean, then, as referred to in the last slide, the crust is very thin. Okay, so here's 0 to 20 kilometers before we get to the mantle of the Earth, and overall a very thin crust, mostly mafic in composition, magnesium and iron silicates, or basalts and gabbros. But we do start to see some small pockets, maybe, of this more felsic crust that's starting to develop. And then as the rains, the outgassing of volcanoes and water vapor is condensed in the atmosphere to create clouds and a meteoric system, rain is chemically weathering the rocks and making sedimentary rocks. So we also have some sedimentary rocks that are developing as well. As far as the Earth record goes, we have virtually no Hadean remnants. Virtually. They're some of the oldest rocks on Earth. The Acasta gneiss, I believe, I think it's late Archean in age. I should have had that piece of information readily available. I want to say that that's 3.2 billion years old. The oldest rock that we know of, metamorphic rock. Now, some of the oldest minerals that we have, some of the oldest minerals, zircon minerals, which are sediments from this time, little sedimentary grains that have been recycled through time, are, I believe, the oldest of those 3.48 or 46 billion years old. So those are getting into the late Hadean, I believe. Okay, okay, point here is we have very thin mafic crust of the Hadean. Mafic rocks made of magnesium and iron are slightly better conductors of heat and electricity than the granites, right? So even this thin crust, cold vacuum of space, hot interior of the Earth, this isn't a whole lot to go through, right? So the Earth is very likely leaking out heat pretty rapidly through this time. Now, this time, the Hadean time period, takes up the first 9 days of our geologic time calendar. So I've kind of blocked those days out here, which you can think of as the development of oceanic crust. Then later, what we have evidence for during the Archean, or your typical Archean oceanic crust, contains a lot more complex chemical materials. It's not just mafic, not just gabbros and basalts and maybe komatiites that are here, but instead you have these TTG, or the G there standing for granodiorites or granites. This is tonalite, trondhjemite, granodiorites, but just let's think of them as granites, okay? Just like this nice piece of Idaho batholith granite here. This is more of a white granite. This is one of the lightest rocks, lowest density rocks that we find on the surface of the Earth. Granites, then, are representative of that lighter chemistry floating up to the top in the previous diagram. And we start to see that by the Archean, that the upper crust of the Earth is becoming more felsic rich, more granitic rich. So we have mafic materials, more sedimentary materials on the top as the Earth's surface is going through weathering processes, and then these large blobs or large magma chambers of the more granitic type of substances. That takes the Archean, takes another 21 days of our geologic time calendar here. Now if we take one big step forward into the next geologic time, the Proterozoic, the Paleo, Meso, and Neoproterozoic, remember the Neoproterozoic we've talked about in context of snowball Earth, the crust looks completely different. Any remnants of oceanic crust that we have, right, any of these what are called ophiolite sequences that are this old, look very, very different than the crust of the Archean and the crust of the Hadean. this is simple stuff here, right? Not much as far as the complex chemistries, but by the time we get to the Proterozoic, lots of felsic material in the crust. So we have felsic granulites, much more of these metamorphosed sediments that would have been these clastic volcanic sediments up here. These have been metamorphosed now, but they're still light materials. They're still materials that formed on the surface of the Earth. So they're not heavy, they're not mafic, they're not stuff that's getting recycled down back into the Earth easily. Instead, this is material that accumulates, even though it's being metamorphosed, it's still accumulating on the surface. And we have left over, then, more felsic metamorphic rocks, schists and gneisses and amphibolites. Now, those aren't necessarily felsic, but they are more they're more felsic than, or well, they're quite felsic. Okay, then blobs of granites and large sedimentary successions. Okay, point here is not only has the crust thickened through time. Okay, these segments of oceanic crust, or even the development of continental crust, we can start to call this now because this is almost all granite. Not only has there been a thickening through time, but there has also been a silicicness through time, right? Or an increasing in the felsic content of the crust of the Earth through time. As if the Earth is getting a better and better insulating layer on the outside, right? It starts out with a lot of heat escaping thin crust. As it gets a thicker and thicker crust, it's better at preserving its own heat through time, right? Again, not to anthropomorphize, but this is like putting on a blanket, right? If you're losing heat and it's cold outside, say you go from a nice warm house and you go outside into the 32-degree Fahrenheit weather and you're starting to get cold, a way to preserve the heat that you have before you get totally frozen is to put on a blanket, to put on an insulator, right? And it seems then that the Earth, as a function of chemistry or of these processes, it has added to its external blanket through time to preserve its own heat. That's the system of tectonics in a nutshell. Really, this seems to be the result of these 3.5 billion years of plate tectonics, is doing something like this, right? Now, that's not a self-generating system, that's not a conscious system at all. Some have argued for this in like the Gaia hypothesis and other Earth system scientists, but let's be non-anthropomorphic here and just look at this as a process. Chemistry, light stuff floats to the top. Heat escapes, but if that chemistry, that light chemistry is an insulator, it's preventing the heat from escaping. So this is the picture that the Earth has created over that time period. And now this type of crust is not all that different from what we see today. So there is an argument in Precambrian geologist land. When did plate tectonics start? When did modern plate tectonics start? And the argument is that Archean and Hadean crust don't look anything like today. They don't look like Proterozoic crust. So sometime in the late Archean into the Proterozoic, we have the beginning of modern day plate tectonics, where we have melt that's being created in the mantle that's accumulating felsic material in the crust. Okay, now, how does this all happen, right? This was a lot of kind of arm waving to show the general big picture here, that the Earth has a crust, and that crust has thickened through time, which has also allowed Earth to preserve its own heat through time, maybe adding to the longevity of the planet, right? Or of to at least the planet being an active tectonic planet. By active tectonic planet, I mean in comparison to something like Mars. Mars had volcanoes at one time. Well, it still has the volcanoes, the remnants, but they're not active anymore. It maybe had a style of plate tectonics, or at least tectonics, because there's faults, but they don't seem to be active, and they haven't been active for a long time. The planet had water, right? Sedimentary rocks have been deposited there. It doesn't have water today. So Mars effectively is a dead tectonic planet. It's not geologically dead. There's still surface geology that's occurring. But it is not active tectonically or volcanically as far as we can tell. So its core, or at least the interior of its mantle, is probably not convecting. Or if there is convection, it's very slow. Or, you know, I'm just speculating here. I'm not a Martian geologist or a Mars studying geologist. But Mars is very much not like the Earth. It is a frozen, dead, tectonically dead planet, as opposed to the Earth, which is still very much alive. So if it is the heat of the interior that keeps convection going, then the longer that heat is preserved by the blankets on the exterior, the longer the Earth will be able to stay tectono-volcanically alive. Okay? So how does all this happen, right? Here's my couple of silly pictures for the day, right? Jackie Chan, how is this happening? And maybe Trump knows. He's kind of got a smirk on his face like, yeah, I know the answer to that question. To which, you know, Obama just laughs hysterically. You know, seems to be the good answer to some of these problems. But what is the mechanism behind this? The mechanisms and functions that we've talked about thus far are heat escaping and chemistry floating, but that's really broad. Now I want to take a step into a little bit more focus, a little bit more geologic focus here, and talk about early plate tectonics and this process of subduction. So, plate tectonics. Enter Alfred Wegener here. This is Alfred Wegener, one of my favorite pictures of the guy. This was on a ship, I believe, on his way to Greenland or Antarctica. And here's smoking his pipe, probably tobacco in there, just if you were wondering. And Alfred Wegener here, he is well known in geology, of course, as the father of the plate tectonic theory, which he never called it plate tectonics. To him, the original unveiling of this idea was called continental drift, to which this idea was not accepted during his lifetime. Okay, he wrote this tremendous, wonderful book. He had given lectures on this, public presentations at conferences, geologic conferences, and this book, The Origins of Continents and Oceans, 1929, I want to say. Okay, this book, though it was published in the scientific literature, and today we see this as the beginnings of the ideas today we call plate tectonic theory, Alfred Wegener never got to see that accepted in his lifetime. This was something that he was marginalized for. This was a wild claim and wild idea that the Earth, the continents move laterally. Okay? Today we take this as for granted, right? That the continents move laterally as plates. But in Alfred Wegener's day, the going hypotheses of tectonics were all vertical. That mountains rise and valleys lower until all the sediment coming off of the mountains lowers the mountains and the basins rebound back up. Okay, so you have a vertical tectonics, or the synclinal theories, geosynclinal theories that dominated global tectonic thinking at this time. Now, Alfred Wegener is a trained meteorologist, from what I understand. He's more of a looking at the sky and observing things. I think generally he's a naturalist that appreciates many natural things, but he had training in meteorology. So here I have him kind of staring off into the clouds here, right? And in these clouds, we have this water vapor system moving in this direction that's overrunning a different density of atmosphere. So this atmosphere here is very dense because it has an increased amount of water within that, and also it has a different temperature associated with it. Now the atmosphere here, slightly different temperature and slightly different atmospheric moisture content. Now those two parcels, what we call what are these pockets of air, what we call, oh my gosh, I'm losing my words here. Okay, let's just call them parcels. These different pockets or parcels of air, where they collide with one another is what we call a front. Okay, just like a weather front. We hear this on the news, right? There's a front coming in, something like this. Or even this style of diagram, these teeth, is what they show on, national or even regional meteorology or weather news, is they show this kind of teeth thing that represents one air mass, that's what I was looking for, overriding the other air mass. So that's what is shown here, is this air mass is overriding this air mass, and at the confluence between them, they're creating action, right? It's where the two things run into each other that there's action. Not way out here in the middle, not way out here in the middle, but right there, where they converge together in this case, there's action going on, okay? This is then what we might call a convergent zone. And in meteorology, this is creating a weather system. Here you have, downpouring rain and a nice rainbow here in the background. So Alfred Wegener, being a trained meteorologist, he's used to looking up in the atmosphere and thinking about different densities of air masses colliding together, creating chaos or creating events, big things going on, right? Hailstorms, tornadoes, even rainstorms, thunderheads, cumulonimbus, all this atmospheric nomenclature. Okay? That's what he's thinking about as he's looking up here in the clouds. Now, as they say, like above, so below. Now, that's not exactly precise here, and that's some kind of funny occult language, but I want to point out that he's looking at the above, and then he directs his attention to the below, right? Or to the below his feet. And in looking at, and once he got some time to look at this, there's a good Cosmos episode, Neil deGrasse Tyson Cosmos episode, that kind of tells the human story of Alfred Wegener a little bit and how he put this hypothesis together. But as he got time to look at maps of the Earth, in the distribution of rocks, distributions of fossils, he started to put together this idea, this first an idea, then he gathered evidence to create this hypothesis that maybe the geometry of the Atlantic Ocean, which, by the time World War I, which Alfred Wegener participated in, post-World War I even, we started to get a lot better maps of the Atlantic margins. Alfred Wegener started, he had this hypothesis that maybe the geometry of Africa and South America and North America and Europe, or the Straits of Gibraltar, that those things fit together like puzzle pieces. And that maybe the continents were actually connected and have drifted apart over time. That's what became known as continental drift. The continents have drifted away. And he called that original piece of land where all the continents were together, he called that Pangaea, right? Or Gaia for the Greek earth goddess, and then Pan for all, or all of Earth together into one continent. So here's Alfred Wegener's original rendition of that, of Pangaea, with Africa here at the center, and South America, and so on and so forth. And then here's a slightly more modern version of what we see today by the rock distribution of what Pangaea likely looked at. Now, as I mentioned, Wegener never saw this come to light, right? Wegener wrote the book. He was sort of marginalized from the geologic community and never was able to see his idea, his hypothesis accepted, and Pangaea was never known to him as a scientifically accepted concept. Where today, this is in children's books, we know this, we have great, lengthy, detailed evidence for this, and also the formation of Pangaea, the breakup of Pangaea, and so on and so forth. Now, we'll get to that a little bit later. Okay, this was one of Alfred Wegener's, one of my personal favorite pieces of his evidence was he looked at rocks on either side of these proposed continents. I mean, why wouldn't you look at rocks, right? And if they were connected then, you would imagine that they would share a distribution of rocks that are similar. And Wagner was able to find that. He was able to look at metamorphic mountain belts, or what we might refer to now as orogens, that shared commonalities between each of these major land masses. Okay, so he would propose that mountain ranges like the Chalcedonies and the Appalachian Mountains were actually the same continuous mountain range that had been broken apart on either side of the Atlantic Ocean. Now, Wagner had imagined these drifting granitic continents away from each other, and that the oceans are separated by these more dense basaltic rocks. Okay? Now, let me back up a second to Alfred Wegener looking up. Density was a really big key in looking at one air mass colliding with another air mass. And to determine what's going to happen between them, density played a big role. How much water vapor does one have, or what is the temperature? Cold stuff is more dense than warm stuff. So density played a big role in this. Wagner, looking at the data that's coming about from around the world, was noticing the continents are mostly granitic in composition, where the oceans are basaltic in composition. Mostly basaltic in composition. So he's also arguing that there's a separation between the more buoyant granitic pieces of the Earth's crust and these lower, more basaltic areas of Earth's crust, and that there's some mechanism, well, he didn't propose a mechanism, but there is this relationship of drifting apart as if these granitic continents are like boats floating over this basaltic, more dense sea. Okay, as the boats are lower density, the water is higher density, and those boats are floating across. Now that was one of the pieces that geologists hated about his hypothesis. Granite continents floating like boats across the ocean? What are you, crazy? So he was a crazy meteorologist. And again, his ideas were marginalized because of this. He had no mechanism to how the granite could be forging its way over and across these basaltic plateaus. Aha! Right? The mechanism comes in that the granite wasn't drifting over these, but instead these basaltic provinces are pushing those granitic provinces away. Okay? So what we see now today, I'm not going to go through the whole theory of plate, the development of the theory of plate tectonics, but one thing I will say is that the key was in during World War II, going back and forth across the Atlantic Ocean. The key was in mapping out the bathymetry and the heat flow of the Atlantic Ocean. Bathymetry, which is basically the topography of the ocean floor, revealed that the mid-ocean were tall mountain ranges, ridges in fact. We call them mid-ocean ridges today. Contrary to what you might have thought, that the middle of the ocean would be the deepest. Also, finding that the highest heat flow is happening at the center or the axis of those ridges. So, the theory of seafloor spreading by Hess was developed, which was tied in with continental drift, together creating the unifying theory of plate tectonics that suggests that these granitic blocks, instead of floating on top of the oceanic basaltic crust, instead are being, the mid-ocean ridges are pushing and creating new oceanic crust that's pushing the edges outward. Okay? And in this case, the subduction, or the oceanic crust, is being subducted beneath continental crust. So there are areas where the continental crust is riding over on top of the oceanic crust, but it's not originally as as thought maybe as the boats climbing across the ocean. Okay, so what does happen here is the mid-ocean ridges that are pulling open, right? They're also being pulled by the subducting crust on the other side. All right, now let me regather myself and back up here for a second. I wanted to finish up kind of the development of the plate tectonic theory there, to lay that down, that the key was in seafloor spreading. But to come back to this image, after Wagner from the 1920s, and then the development of the plate tectonic theory by the late 1960s, now we have this really good working hypothesis that we compare everything back to, that we now call a theory, right? The theory of plate tectonics, because all bits of evidence point back to that hypothesis, this global system of tectonic plates, or kind of like a dinner plate. They're these individual pieces that on the edges of them, if you're shifting them around the dining table, it's on the edges of those where they interact that there's action that's happening. Earthquakes, volcanoes, this type of stuff. Okay, so we have today identified 3 major types of tectonic boundaries, or 3 types of scenarios that the plates can undergo, right? Either they slide past one another. That would be like a transform fault or a transform boundary, which can be shown right here. They're not all that common in the really large context, mostly here at the mid-ocean ridges that are offsetting the rate at which this one is going that way and this one is going that way. Okay, so they're offsetting those rates a little bit. Also, the San Andreas Fault on the west coast of North America, or the Anatolian Fault that runs through Turkey. These are also large transform faults that happen to also intersect bits of continental crust, or on land. So we have the interaction where dinner plates can slide past one another, or they can diverge away from one another. They can separate from one another, and that's what's happening here at a divergent plate boundary, where these 2 oceanic plates are moving away from one another. Okay, and then the third possible interaction, if things aren't moving past each other, things aren't diverging away from each other, things are crashing into one another, right? And at that crashing, we call those converging boundaries then. They're converging together. And of those converging types of boundaries, there's then a couple of scenarios depending on the type of crust. You can have bits of oceanic crust which are colliding with or converging with other bits of oceanic crust. You can have oceanic crust that's converging with continental crust. Now naturally, the continental crust is much more buoyant, right? It's a granite, it's a lower density material. So the oceanic crust subducts beneath. And the third possible scenario, it's not shown up here, is if you have a piece of continental crust that's converging with another piece of continental crust. So that you have these 2 buoyant pieces of crust that are locked together to make a collisional plate boundary, or a mountain range plate boundary. This is what's happening at the northern end of India that's running into Asia, and you have the Himalayas, or the Himalayan plateau, the Tibetan plateau there. Okay, so now we have these major 3 tectonic boundaries, but also, besides what we can see on the surface of the Earth, we can also think about this at depth, in the context of our layered Earth, right? Remember that the light chemicals are floating to the top. We'll look at that mechanism in a minute. But also, heat is escaping, right? That heat that's escaping from the interior towards the exterior is creating this tumultuous convection within the interior of the Earth. As heat is welling up, right, or the hot material down below is trying to move upwards, cold material then is settling downward. So there's a replacement of cold going down and warm going up, just like a boiling pot of water. If you have a pot of water on a heating element, the bottom of it heats up, and that hot water becomes buoyant and moves up to the surface. And the cold water densely settles down to become heated up. So we have what's hypothesized is these great convection cells. Now, these bicycle wheels probably aren't exactly the scenario, but these are just diagrammatic arrows to suggest that we have this convecting cell, this boiling pot of material. Remember, it's not liquid, but this boiling type of action in the interior of the Earth. And it's that process then that is thought to drive plate tectonics. This boiling of heat coming up that then maybe rises these mid-ocean ridges that separates these plates. Okay, now I want to come back to the other side of the convecting cell, the boiling upwards. That might be important, but also the downgoing cool stuff. It seems now we're agreeing that is probably much more important than the warm stuff coming up. That the cold stuff going down, the subducting plates going down, is also a big driver in plate tectonics. Why? Because it's the pulling, the slab pull, this cold stuff going into the mantle of the Earth, that is actually pulling on these mid-ocean ridges. And that pulling is allowing the heat to moltenly upwell on the upper mantle. So maybe this hot stuff that's upwelling at these areas isn't part of the big bicycle wheel. Okay, instead, this is going down as cold, and the stuff that comes up to replace the cold, the hot mantle plumes, which we'll talk about later in class. Okay, all right, spent too long on this diagram here. I'm getting a little bit too wordy. Continental rifting, converging oceanic crust, converging oceanic and continental crust. Okay, this type of tectonism, the plate boundaries, it's what's driving volcanism. Okay, this is business as usual. This is how the Earth functions. Driving volcanism, most volcanism. Okay, those things I just mentioned, the mantle plumes, those also drive a different style of volcanism, intraplate volcanism. We'll get to a little bit later. All right, so let's look at some of these mechanisms there. How does this process of chemicals floating and heat escaping, how does this actually manifest on the surface? Right? It's great to throw our arms around it and say this, but what is actually happening at the minute scale? And here I've zoomed into the diverging plate boundary. And what's happening here, as rock, remember the mantle is solid, as rock goes from this place to this place, right? This is going from a deeper level to a shallower level, from higher pressures to lower pressures, right? What's happening here is this material is undergoing a decompression, right? If this is under a whole lot of weight, a whole lot of lithostatic weight on it, but then it moves up under this driving force, right, this convective driving force, and it moves up, it's getting decompressed. Okay, this is kind of like a balloon, a helium balloon that's going up into the atmosphere, or a weather balloon, right? It starts out yay big. Well, you know, weather balloons are pretty big. But it gets up into the upper atmosphere, and that gas begins to expand, and it gets bigger and bigger and bigger. It's decompressing through time. Another way to think of this, and this is my favorite analogy, is a propane tank. You have a propane cylinder. You go to the gas station, you fill that stuff up with propane, and you shake it in there, and you can hear that there's liquid in there, right? But what do when you unscrew the valve, and gas comes out? What you've done is take the pressure off of that liquid, and the liquid has changed phases from a liquid to a gas. Okay? Now, this isn't that different. So this happens, goes up. That's just like taking the pressure release valve and decompressing this solid material to make a little bit of liquid material. Okay, this is what's called decompression melting. Melting as a process of simply taking off the pressure. And that forces some of the minerals in this rock, the peridotite of the mantle, remember the green mineral, olivine, forces some of that material to undergo a melting regime at these temperatures. Okay? But it's a very specific range that happens in here. It's not like the whole rock is melting. It's just a small percent, maybe 2% of the overall rock is undergoing melting. But 2% at the amount of this stuff that's going through this process, 2% of that is enough to create huge magma batches. Remember that liquid then, Liquid is more buoyant than the solids around it, and that begins to buoyantly rise upwards and coalesce into larger and larger chambers of magma. So the rifting area results in this very specific sequence of decompression melting, starting with the heat, but resulting as a compositional change, right? So this is heat driven, but the result is light chemistry floats to the top. So this is tying in the compositional and the mechanical layers in this process of heat escaping and chemistry, light chemistry floating to the top. Let's look at this sequence a little bit more closely. So here's the sequence, the ophiolite sequence. Okay, first of all, under DC, okay, so we are in, we're under the ocean here in the oceanic crust. Excuse me. We're going to fill this space in with the rest of that diagram, the rest of those rocks. First of all, we're under the sea. Here's a mid-ocean ridge with a little bit of molten material showing that this is the divergent plate boundary. Here's, you know, aerial for scale. Well, not really for scale. This is not to scale. Then we have the peridotite, the mantle peridotite below. Remember, this is the greenish rock. I showed during the first week when we were looking at rock materials. Now the outside here is yellow, that's a weathering rind. Okay, but the interior here, this non-weathered stuff, is a green material, olivine, the green mafic mineral made of magnesium and iron silicates. That makes up most of the mantle of the earth, remember. This peridotite material, first of all, if we have raw, unadulterated peridotite, we can call that fertile peridotite or fertile mantle. What that means in this context is that that is fertile with all of the other stuff that could be melted out of it, okay? So I kind of think of it like a sponge that's full of water, is that it's fertile with water still, okay? And what's happening here in the ophiolite sequence, as the peridotite undergoes decompression, the water is being allowed to drip out of there, to squeeze out of there, and it leaves behind the spongy material, leaves behind the rest of that composition. So we have fertile mantle undergoes that decompression process, and what comes out of that then is the magma chamber. Okay, now it's magma that's the composition of basalt. Now remember, basalt is one of the more mafic lavas, the more mafic materials on the surface of the earth, and the intrusive counterpart, or the basalt that forms on the interior of the earth, remember, is a gabbro. So we have a magma chamber as the molten material is squeezed out of the fertile peridotite. We end up with gabbro, gabbroic magma chambers. And some of that gabbro, as it sits here in this magma chamber, some of those minerals that are forming, they're very heavy. They're made of magnesium and iron silicates. So they can accumulate down towards the base of that. And we call that a mafic accumulant. Okay? Now it's important to also show, well, what was left behind, right? If you have fertile peridotite, and then you take this stuff out, then there has to be other stuff that's left behind there, right? And that's what we call the depleted mantle, okay? So we have depleted mantle, the mafic accumulant, the gabbroic magma chamber, and this is how we can see, or I hope you can see now, why we call this a sequence, the ophiolite sequence. The sequence is not only in the sequential package of rock, but also that each successive layer has origins in the layer below it. So it's a sequence of formation, not just a sequence of rocks, but a sequence of formation. Fertile peridotite, depleted peridotite, the mafic accumulant layer at the bottom of the gabbroic magma chamber. But then that magma, remember, liquids are buoyant, they're hot, the liquid is more buoyant than the solid stuff around it, so the liquid's going to want to float upwards, and that, as it's floating upwards, occurs through what's called a magma dike. Okay, a dike forms to allow that magma to go from the interior of the gabbro, or the interior of the magma chamber, up towards the surface, And as it erupts out on the surface into the ocean, that's really cold water. So that hot magma next to the cold water makes these pillow lavas. And here's a nice little animation, or a nice little GIF that shows one of these pillows forming off the coast of Hawaii. The lava, as it's flowing, the outside of it is cooling rapidly, but as the lava is flowing, it's forcing it to expand more and more and more, and it makes these really long tube-like features. Of course, they're not tubes, they're filled with lava, wormy tube-like features, but when you cut them in half, they look like these round bicycle wheel things, okay? So pillow lavas, or pillow basalts, as the magma erupts as lava on the surface of the bottom of the ocean. Okay, so this is what's called then the ophiolite sequence, or making of the oceanic crust. Okay, starts out with decompression melting as the plate is pulling apart, and then sequentially these rocks form. Now, at the very top of this, I'm not going to go through the rest of this sequence, but sedimentary rocks are then deposited on top of those. Those are the layered things here. And then also these features called black smokers. Maybe you've read of these or seen these. The material that's billowing out of those is the mineral galena. It's a lead sulfide. And they appear to be just like black billowing smoke, black smokers. And that deposits these volcanogenic massive sulfide deposits, or copper deposits. Now, those I'm not going to go into, at least in Violent Earth. Okay? Now, the point here, remember, today we're making crust. Back in the Archean and the Hadean, that take up most of the early parts of geologic time, this is business as usual. This is how crust was likely forming on the Earth. It was hot stuff bubbling upwards and undergoing decompression, melting, and making this sequence. Now, the difference between the Archean style of tectonics that's driven probably by heat rising is that the Proterozoic type of tectonics are driven then by cold stuff sinking back into the mantle. And that's the next melting process that we're going to get to. Okay, but let's finish up here with the ophiolite sequence. I wanted to then put this in kind of a sequence here. If you rip across, or if you rip apart the ophiolite sequence, decompression melting occurs, and this fills in with more ophiolite. Okay, and so on and so forth. Every time this opens more, it's filled in more. Opens more, filled in more. Opens more, filled in more. It's not necessarily filled with lava, right? We don't necessarily need to think of it like that, but it's filled from the bottom upwards with this material, okay? So the rifting process creates a particular type of melting called decompression melting. Now, let's go over here then and look at where the converging oceanic and continental crust are creating more molten material over here, right? Now, this is more like normal style or modern day plate tectonics in the Proterozoic with cold stuff sinking. Okay, the process here of subduction, just some global background here. This is the same basic image we were looking at a minute ago with the downgoing oceanic plate underneath the continental plate. They're converging together, and that's creating molten material here. Now, this is the part that I want to focus on in the subduction process, okay? Now, the subduction process is globally very, very important. If you've heard of the Ring of Fire, right, the whole Pacific Ocean is lined by these subduction zones. You have most of the west coast of South America, where the Nazca Plate is subducting underneath the South American Plate, and portions of the Cocos Plate underneath Central America. And then also up here in the Pacific Northwest, we have the remnants of a more ancient plate, or today what's called the Juan de Fuca Plate, that's subducting beneath Northern California, Oregon, Washington, and British Columbia. And then also the Pacific Plate subducting beneath this other portion of the North American Plate to make the Aleutian Islands here in Alaska. Then all the way down then the western Pacific as well. The Japan arc, the Marianas Islands, the Tonga arc, the Indonesian arc. Subduction on every side of the Pacific plate. Now, that's also driven by, remember, as it's being pulled apart, there's stuff opening in the middle. So there's actually mid-ocean ridges in all of this, like the East Pacific Rise, that again are pulling apart and allowing decompression melting. Okay, point here by showing the map is just to show how globally distributed subduction is, and it's very important for volcanism on the surface, but as we will see, this is also very important for making granitic crust. Now, the last process that we just went through of decompression melting, what was the result, right? The result was this stuff, oceanic crust, which is mostly basaltic or mostly mafic. Mafic rocks aren't any good at holding in heat. Well, okay, they're fine at holding in heat, whatever. But granite rocks are better at holding in heat. So, again, if you go from inside to outside in freezing weather, and you take a thin blanket, I don't know, like a thin blanket, that one doesn't hold in heat so well. But if you take a thick wool blanket, that one holds in heat very well. And that's going to be the difference here between oceanic crust and granitic crust. The heat flow here, much more heat flowing through the oceanic crust than flowing through the continental crust. So at the subducting plate boundaries where oceanic crust is subducting into the Earth's mantle, first of all, this oceanic plate here, it's called an oceanic plate because that's what's underneath the ocean, these basaltic plates. So naturally there's some water that is filtered through the cracks in this oceanic plate. So there's some amount of free water that's there. Also, the minerals that make up this basaltic material and some of this depleted peridotite that makes up the rest of the lithosphere also has within it minerals, some minerals that contain water in their crystalline structure. Some minerals like amphiboles and micas. As those minerals and the free water are subducted down into the mantle, at about 100 kilometers depth, that water is dehydrated away from the plate. So this is as if the water is getting too hot to be part of those minerals anymore, and it volatilizes away. It becomes free material away from the solids, and that causes then a lowering in the melting temperature of the surrounding mantle peridotite. Okay, so let's back up here a second. Again, what I'm saying here is the water that's coming down with this subducting plate is going into the mantle. It's dehydrating or being driven off into the mantle. Okay, the redder area over here that's mostly olivine, remember? And as that water is introduced, that new chemistry is introduced into the mantle here, because it's changed chemistry, has no choice but to undergo a melting process called flux melting. Okay? Okay, let me back up. This sounds really weird, right? How does adding water to rock make melt? Okay, you're probably asking this. I know what I would ask this. I did ask this. Okay? All we're talking about here, just like decompressing that propane cylinder to make liquid into a gas, all we're talking about is a phase change, going from a solid into a liquid. For instance, when it's frozen outside and the sidewalks are icy, we could chip off the ice. That's one way to get it off. But what's another way? You put de-icer on, right? All you do is put a chemical on that material, or salt, and you change the chemistry of the ice and of the water to allow the melting temperature to decrease. So it starts out freezing is 32 degrees. You throw some salt on there. Now freezing is down here at, say, 26 degrees. So you end up melting some of that ice by only changing the surrounding chemistry. Okay, that's what's known as flux melting. It's a beautiful process. It's really cool. Something we use in in our everyday lives with salt out on the sidewalk. Or if you've ever heard of when you're boiling a pot of water, if you dump salt in the water, same thing. That lowers the melting temperature, in this case the boiling temperature of the water, so the water may boil faster. Okay? Now it turns out that you need to add a whole lot of salt to really change that very much, but the salt tastes good anyway, so let's just keep doing it. Alright, so back to the diagram here. The oceanic plate puts water that's with the oceanic plate, water subducts into the mantle, dehydrates into the surrounding mantle that undergoes flux melting, creating a small amount of melt, same type of melt where we have the peridotite and the fertile peridotite and gabbro or basaltic composition is being extracted from that, okay? And that composition, that basaltic composition, liquid, buoyantly rises upwards, okay? And eventually, once some of that material makes it all the way to the surface, becomes a volcano or volcanism, Mount St. Helens. Okay, this is what's occurring here on the west coast of North America, at least at my latitude in Oregon. You have the Juan de Fuca plate that's subducting beneath Northern California, Oregon, Washington, British Columbia, causing flux melting in the mantle that then creates molten material that eventually becomes volcanoes like Mount Hood or Mount St. Helens. Okay? Now I want to point out one thing here, a very common misconception. I don't want to dwell on this. What is not happening, the plate is not getting subducted and then melting away because the mantle's hot and coming up as a volcano. Okay? Not happening. The plate continues to go down into the mantle, and I'll show you some seismic evidence for this at some point. Some seismic imaging shows that these great slabs of rock, they just keep going deeper and deeper and deeper and deeper into the mantle until they hit the core. Okay? They go all the way down to the core mantle boundary, where there's a slab graveyard down there of these ancient slabs. Now down there they may get heated up and buoyantly rise back upwards as mantle plumes. We'll talk about that later. Point here is the subducting slab is dehydrating water, and the water lowers the melting temperature to make volcanism. Okay? This volcanism produces basalt initially, but as that basalt undergoes magma differentiation processes, it may get more silicic through time. So here's our varieties of volcanic rocks, or the types of rocks that could potentially come out of volcanoes. If we go collect rocks around a volcano, this is the types of rocks that we see in increasing amount of silica dioxide. First of all, here's those basalts. They're dark in color. Add a little bit more silica dioxide, you have andesites. Add a little bit more silica dioxide, you have rhyolites. This is a picture by Marley Miller, marleymillerphoto.com. She has some great geology photos on there, and I scanned this off of there quite a while back. This is in order from more mafic material to the more silicic rich material. Remember the mineral bins that we did during the first week, where we have the mafics like olivine and pyroxene, the aluminosilicates like the feldspars, and then the more pure silica stuff down here like the quartz. So we expect to see quartz in the rhyolitic rocks and olivines in the basaltic rocks. Okay, alright, we made it back to this diagram. So, the layered earth, it's one thing to think about it as a layered earth and then to even see the seismic evidence for this. It's quite another to see the mechanism at how this is occurring through time. How is the chemistry floating towards the top? It's not just randomly floating and going up to the, it's happening through mechanisms of melting at the surface. We have iron and magnesium silicates that make up the mantle of the earth, but then at the very top, some of those minerals undergo melting, and the lighter chemistries, the potassiums, the calciums, the sodiums, the aluminum, gets trapped in the melt to become solid on the surface that makes up the granitic crust, or sorry, the continental crust and the oceanic crust. Then also, another part of that mechanism, the whole reason that this stuff occurs is because heat is trying to escape from the interior to the exterior. Now, during modern day plate tectonics, because this process has gone on for 3+ billion years, we now have very thick continental crust that's serving as kind of an insulating blanket to slowing the pace of heat dissipating from the interior of the Earth to the cold vacuum of space. Okay? I'm probably overstating that last bit, okay, that the heat flow over the last 3 billion years has had a huge change. I know there has been a change, but it is not a striking change. It's not a huge change from one moment there was a lot of heat and then it put on a blanket and now there's no heat. It's not like that. It's a slow, gradual change and a decreasing amount of heat flow from the interior. Also, the Earth has cooled since that time, right? Since the Archean. Archean, hotter Earth, thinner crust, more heat flow. Proterozoic, Paleozoic, cooler Earth, thicker blanket, less heat flow. Okay, so there's multiple parts to that scenario. I don't want to overplay the anthropomorphic idea that the Earth is covering itself with a silicic blanket to preserve its own heat, but I think it's a good way in our Violent Earth class to think about that. Okay, so what we've gone through here is that the light compositions of rocks remain on the surface of the planet in an ever-increasing amount via volcanism. So now that's the next part of this video. We'll go ahead and take a pause and talk a little bit about volcanism. Coffee. Okay, we're back. This is where we left off. Kind of a long break, at least to me. All right, so we left off, well, you know exactly where we left off because it was just like 30 seconds ago to you, but we're making crust here. We're making crust, and what's important here is that's all happening through volcanism, right? It seems violent to us, but this is Earth's business as usual. All right, a few minutes ago we talked about this kind of convergent zone, an oceanic plate underneath a continental plate, and gave the example of that actually happening here at the Cascadian Arc, or on the making the Cascade volcanic range. So here's the Juan de Fuca plate that is diverging away from the Pacific plate, but it is also converging with the North American plate. And as that subducts into the mantle, dehydrates, undergoes flux melting, and some of that molten material buoyantly rises upwards to become the Cascade volcanic arc. And that's also shown here in 3 dimensions, right? If the map view doesn't work for you, here's the diverging plate, subduction into the mantle, hot water is released, and that creates flux melting, creating volcanism. So the Cascade volcanic arc right here in at least my backyard, not all that far away. I live or am broadcasting over here from Ontario, Oregon, in the Treasure Valley area. But really, the volcanism is really not very far away, making one of the iconic volcanoes of the state, Mount Hood, just outside of the great city Portland. Then also we have Mount St. Helens to the north, just on the other side of the Columbia River. This is a more modern view, recent view of Mount St. Helens. It's much more flat-topped now than pre-1980, which of course used to be a much more pointy-looking volcano, like this. This is a picture of Mount St. Helens in 1979, a nice pointy volcano, the epitome of a stratocone volcano, or also called a composite cone, because it's composed of 2 major types of volcanic material. Either your kind of andesite lava flows, or even some basaltic lava flows out of the base, and then some pyroclastic eruptions, or some ashy type eruptions, and then it's the glue and the powder, glue, powder, glue, powder, glue, powder, that kind of make up these steep edges to a stratocone volcano or a composite cone volcano. Now, in 1979, Mount St. Helens looked like this. A mere couple years later, looked like this when Mount St. Helens blew her top. And very famous volcano. This is elaborated in other places. I think here in our violent context in Violent Earth, I'm not going to elaborate in the story of Mount St. Helens too much, other than showing these devastating pictures like this, showing that the entire mountain lost its top. It literally blew its top. Well, actually, there's a landslide off to the north side, and that landslide began to uncover or to allow that magma chamber to even undergo further, not decompression melting, but decompress a little bit, and that helped it blow more of that top into a very violent eruption. Now, this violent eruption here, you know, very amazing picture, just amazing, really shows up close that violence that we're talking about, this immense, powerful force. In this event, there was a cubic kilometer of rock that was ejected out of the volcano. Okay, cubic kilometer. So cubic meter, let's see, like a meter is about like this, right? There's 1 meter by about a meter tall, by about a meter deep. I mean, that's a huge slab of rock that we're talking about, 1 cubic meter. And we're talking about 1,000 of those, right? To make a cubic kilometer, it needs to be those, 1,000 in that way, 1,000 in that way, and 1,000 in that way, right? So we're talking 3,000 of these blocks to make a cubic kilometer of material. So a kilometer, let's see, if you're used to running track or something like this, this is the best analogy, or at least the distance analogy that I can think of. So you have a 100-meter dash, right? That gets you from one side of the track to another. So you need 10 of those, right? So that distance is a kilometer, and so kilometers, it's not a mile, right? It's about 1/3 of a mile, but a kilometer is a pretty immense length. And then if you imagine that cubic rock that I'm holding right here, and that length and in that length, this is a huge amount of material that we're talking about here. Probably, you know, a good chunk of the size of downtown Ontario or something like this. Or this is, say, like a huge chunk of downtown Portland. A cubic kilometer of rock was ejected from this volcano. Okay, that's just the rock. Now, the gases that were expelled, I mean, that's a whole lot of material. That's the gases that are expanding that drive a lot of this billowing volcanism of the rock being ejected up into the atmosphere. But take out all the gases, take out all that stuff, and condense it down into rock. Best estimates show about a cubic kilometer of rock was ejected. 1 cubic kilometer of ash. Okay, now let's talk about another famous eruption, Mount Pinatubo, 1991 in the Philippines. Okay, did I say 1992? 1991 in the Philippines. Massive eruption, right? This is from, you know, probably 10, 15 kilometers away from the volcano. Boom, right? Huge billowing eruption way up into the upper troposphere, probably reaching the lower limits of the stratosphere as it erupts above the tropopause and spreads ash all over. This volcano released 10 times the amount of Mount St. Helens, 10 cubic kilometers. Okay, so there's that 1,000 cubic meters, times 10 of that. Okay, a massive amount of material ejected from this volcano, and this happened in our lifetime-ish. Depends on the age of which you are that you're watching this, but I'm 33 years old, born in 1985, and this was within my lifetime. I don't remember it, right? I was only 6 years old, but this is an event that isn't all that long ago, or even if you were born, say, in 1996, right? This is still within, you know, our really modern time. Now let's look at a few more ancient eruptions, or not quite in our lived history, so your grandparents aren't going to remember this one, but a larger volcano, Krakatoa, Okay, Krakatoa in Indonesia in 1883. This is also known as the island, the volcano that blew up its own island, that blew itself to smithereens. Okay, so during the Indian spice trade, right, the Indonesian archipelago was fairly well known and fairly well mapped out, and boats traveling in this area before the eruption had noticed, right, here's the size of the island chain of Krakatoa, this middle island here, and the volcano of Krakatoa, boom, blew its top, and now nothing, right? The entire island blew up, right? This released 18 times the size of Mount St. Helens. 18 cubic kilometers. Boom! One eruption. The eruption heard throughout the world. And this eruption also in 1883, the summer of 1884, and I think also 1885, I'm not a great history buff, like human history, but I think that both of those summers were associated with maybe not necessarily famine, but agricultural failures, because the amount of sulfur dioxide that was put into the atmosphere caused a global cooling to occur that made the agricultural season worse. Okay, then let's go back even further in time. Another very famous eruption, the eruption of Mount Vesuvius in Greece in 79 BCE, or before the Common Era, or AD. This released 75 cubic kilometers. 75 times the size of Mount St. Helens, okay? All right, Mount St. Helens was big. That's what we started off with, and that's a big, important volcano, or big, important eruption in American history, right? This is in my backyard where I live today. I didn't live in the Pacific Northwest at that time. In fact, I wasn't alive at that time, right, 1980. But this eruption, if you were alive at that time, it's very well known around the United States of the inhabitants. It's very well documented leading up to the event and after the event and so on and so forth. Also, well known in the archaeologic history is, of course, the Vesuvius eruption. Why? Because in the shadow of Mount Vesuvius, Pompeii, the ancient city of Pompeii, that was destroyed in this eruption. At that city in Pompeii are these mummified people that are still that are entombed, or that are encased in the ash of that volcano. Now, they're not really mummies. Okay, this is probably a little bit more gross than mummification, but the blast from this, the pyroclastic flow, the hot, fiery ash flow from this, the Nuée Ardente, the flowing down the landscape, this is an ash cloud. And remember, ash is made of small shards of glass. They're small shards of, so they're sharp little things anyway. But this is a fiery ash flow. This is thousands of degrees Celsius, okay, or well, thousands of degrees Fahrenheit, excuse me, in Fahrenheit, probably, what, 400 degrees Celsius. This is hot stuff, a hot, fiery ash flow, a glowing cloud racing across the landscape, and there's nowhere to run, right? You can't go anywhere, you can't outrun this thing. This is moving at 125 kilometers an hour or more. And this fiery ash cloud, as it's coming towards you, it's hot. And remember, your body's made of water. What happens when water gets really hot? It turns into steam, it volatilizes, it expands. Okay, so imagine your body, your water-laden body, this oncoming pyroclastic ash flow heats up your body all at once and volatilizes you, and poof. Okay? The people literally, very likely, exploded into steam, fleshy, bloody steam. And that material is what glued together the ash, which left these almost sculpture-looking remnants of the people of Pompeii. Okay? Ugh. All right, so we have Vesuvius, 75 cubic kilometers of ash ejected from that thing. Okay, we're just getting started here, all right? These are big volcanic events. I just started with famous ones, right? Maybe you've read the book about Krakatoa. There's a There's a book, I can't remember the name of the author or the book right now. There's also, of course, a movie about Pompeii, a Hollywood movie about this. It's got a love story. It's pretty cute. And this is fairly, well known in history because of the amazing preservation of the city under the ash. And then, of course, Mount St. Helens is also well known in the as an American icon. Another American icon that you might not know quite as well, I'm living here in the state of Oregon, it's certainly the jewel of the Cascades, sometimes this is called, but Mount Mazama, or here on Turtle Island, as the indigenous North Americans kind of refer to North America, Turtle Island, maybe you've heard this, and this is long before our written record, European occupation in North America. But there's good oral traditions and the oral record of this by the indigenous people here in the Pacific Northwest about 7,600 BC, okay? BCE, 7,600 BCE, this mountain that was well known to the indigenous people here also blew its top. Blew its top in a huge, amazing eruption, and the ash can actually be seen all over eastern Oregon. If you go visit the Christmas Valley area, Christmas Valley is a wonderful area that I like to go, there is ash still on the landscape, little yellow bits of pumice that are leftover remnants from this eruption. They can be found in lakes out here in eastern Oregon, and the further you go towards the Cascades, there's areas in the Cascades of huge, thick sections of this ash that's left over from this eruption. Again, 75 cubic kilometers of material ejected from this. This is modern-day Crater Lake, the jewel of the Cascades. So this island, or this volcano, blew its top and formed a crater on the top, or formed actually a caldera as the interior of the volcano. The magma chamber was evacuated and the top collapsed down on top of itself to make a volcanic caldera, not just a crater. Okay, Mount Mazama. Oh, look, yeah, there we are. This is my daughter Neva over there at Crater Lake a couple of years ago. Hi, Neve. All right, now, slightly larger, all right, is kind of an obscure eruption, but still historical. This is 1815, another one of these volcanic sequences followed by famine, at least, if not famine, agricultural failure because of this eruption. Tambora, also in Indonesia. This is a painting, J.M. William Turner, showing kind of a rendition of this. Again, this is in literature. This is a well-known eruption to Europeans. And here we have 145 cubic kilometers erupted. 145 times the Mount St. Helens eruption. Okay, these things are huge, amazingly huge. This is from Pinatubo, fairly close to this eruption. This is that hot, fiery ash cloud I'm talking about, right? The pyroclastic flow that's running down the side of the volcano in this billowy, fiery ash that's consuming everything and knocking everything down in its way. Now, this looks violent, right? This looks like, oh my gosh, death is upon me, right? Actually, I don't know this for sure, but I have heard that whoever was driving this vehicle and taking this picture, that they lived, right? That they are still around. But anyway, besides that, this looks ominous, right? I do not want to be standing here. This looks very violent. The epitome of this class then, right? Violent Earth. Boom! This is a good picture of that. But, okay, violent, yeah, right? To the human eye, sort of, okay? Within the context of us, of humans, this is a magnificently violent event, right? In our space and time, yes, but this is business as usual for the Earth. The whole last part of this lecture, the making of crust, right, where we have divergent plate boundaries, decompression melting, and flux melting, making granitic crust over the last 3.5 billion years of Earth history, is this. This is the way that it happens, okay? Now, yeah, there's a lot of plumbing, there's a lot of stuff that's happening down here where granite is also freezing intrusively as large magma chambers. But this is business as usual. This is how the Earth operates. So yes, it's violent to us and extreme. But this is barely the tip of the iceberg for the violent stuff we're talking about in this class. The exceptional violent, punctuated events that have destroyed portions of this planet. Things like snowball Earth, that the Earth was locked in glaciation for tens of millions of years, ice cold, miles high, thick ice. That's cold violence, if you ask me. Okay, so let's keep going with violent volcanism. Here we have 1 cubic kilometer, Mount St. Helens, 10 cubic kilometers, Mount Pinatubo, 18 cubic kilometers, Krakatoa, 25 cubic kilometers, Vesuvius, Turtle Island, 75 cubic kilometers of ash here in Crater Lake, 145 cubic kilometers, Tambora. Together, that's about 275 cubic kilometers of material in this set of eruptions that we're talking about. Now, that's a lot of material. I want to take a slight tangent here and talk about if this was instead oil. Okay, if we take all that volume of stuff and we instead think about that as the volume of oil, right? Now, oil is a substance, right, you and I are fairly familiar with, being, you know, humans in the industrial age, the modern industrial age. We use this stuff to drive our cars around, right? Where oil, a barrel of oil, is distilled into multiple parts, and about 20 gallons of this 45-gallon barrel of oil is used for gasoline that you and I drive around in. Okay, so in a barrel of oil, that's about 0.16 cubic meters of liquid material. We use, and this was data I think from 2016, we use about 96 million barrels per day of oil. Global society, 96 million of these barrels. So 96 million times 0.16 meters cubed. That's about this many cubic kilometers per day then. Okay, it's a very small, minuscule number. 15,360,000 cubic meters per day. Okay, a small amount of cubic kilometers. So how many days would it take to equal that amount of volcanism? How many days does it take for us to consume the oil that makes up the same amount of volcanic land that we just talked about? I know this is a funny tangent here. It's about 17,000 days, or about 48 years. At the rate that we've been burning petroleum, at least since 2016, now this number, if we go back to say 2012 numbers, this is 76 million barrels per year. But at our current rates, it takes about 50 years to do what volcanism has done by ash, volcanic ash, over these last couple hundred years, right? The earliest volcano we were looking at was 75 AD. Or I guess we also did look at Mount Mazama, which is back 7,600. All right. Now, I know that was a weird little tangent, but I just wanted to kind of put it into comparison on the substance that you use every day, oil, and this extreme volcanism here. And the oil thing is a little primer to a subject we're going to get to at the very end of class, which has a lot more to do with you and I and our relationship with the Earth's resources and materials. Now, this image shows the things we were just talking about. The business as usual volcanoes are just volcanoes. They're just normal volcanoes, stratovolcanoes, okay? Quite different from the things that we consider super volcanoes. Okay, here's Mount St. Helens up at the top, little cube. Okay, Mount Pinatubo, slightly bigger cube, 10 times that size. Down to Vesuvius, Tambora, that one we talked about, 145 cubic kilometers. Now Yellowstone, 250 cubic kilometers. This is an eruption a little over 1 million years ago. Okay, now look at the bigger cubes down here. This is what we're talking about with super volcanic eruptions. Thousands of cubic kilometers in one eruption. Okay, this last one, this Mount St. Helens one from a little over 1 million years ago, 250 cubic kilometers, boom, all at once, right? Well, maybe over the period of a couple of days, right? From what people can probably calculate and look at, I mean, there's got to be a threshold to how quickly this stuff is happening. But let's just say geologic time, boom, blink of an eye. Remember, we looked through, what, 6 volcanic eruptions right there, and that equaled 275 cubic kilometers through 6 different big eruptions, okay? This is what I would consider in this class extreme violence. Violence that punctuates the whole functioning of Earth. If the Krakatoa and the Tambora eruptions in 1850 or 1815 and 1875 or 1881 respectively could cause agricultural failures because of the amount of ash or the amount of volatiles and gases put into the atmosphere, think of what this does, right? This can totally change the atmospheric conditions and biospheric conditions of life in general, really changing the Earth system. Yellowstone eruption 2 million years ago, 2,500 million cubic kilometers. Okay? This is multiple times all of the volcanoes that we were talking about. 10 times those 6 volcanic eruptions that took place over a couple hundred years. Toba in Indonesia, another huge supervolcano, 2,800 cubic kilometers in one of its eruptions that we can see by looking at all of the geologic evidence, all of the layers that are out there of ash that are still around, and calculating all of these up and getting our best estimate as geologists how much came out of that volcano. Thousands. Almost 3,000 cubic kilometers. Almost 3,000 the size of Mount St. Helens. That is violent. Okay? So we'll do supervolcanoes a little bit later in the class. Those are large historical eruptions we talked about before. Supervolcanism is violent. Okay? Now, we, of course, this diagram again. Geez, what is it going to do? Talk about it for 15 minutes? Yes. This is where we started, and this is, I just want to come back to this after the volcanism. It is volcanism, business as usual, that is allowing the heat to escape, that's allowing the chemistry of Earth to differentiate into the lighter materials at the top, that's emplacing granites in the interior of the crust, and allowing volcanic products to come out of the outside to make new land and landforms. Okay? And then it is these two processes together that are preserving the heat of the interior of the Earth. Okay? So we don't become an old, cold, dead planet like Mars, right? All right. So the light compositions of rocks remain on the surface of the planet in an ever-increasing amount, right? That's what led us into volcanism. So the light stuff blows out of the volcanoes with gases, of course. The light stuff here is rising to the surface, where the dense stuff stays down here, right? Remember the depleted peridotite, it stays in the mantle, so we have a depleted upper mantle. And then also this dense stuff that becomes the depleted mantle of the oceanic crust, of the oceanic lithosphere, and then this dense basaltic crust here, as that drifts away from the mid-ocean ridge and it cools down and becomes more dense, even that stuff sinks back into the mantle. So really the only stuff that's left over is the extremely light stuff, right? This, the granitic emplacement here, the volcanic products on the surface, the sedimentary rocks that are created by the weathering of all of this system and dumped maybe into the ocean. These sediments, they don't do anything. Maybe some of them get subducted with this, but not very much, right? That's just light felsic stuff on the tip that gets metamorphosed down here in the accretionary prism. So what's happening here is that the light stuff stays on the top surface of the Earth. So look at this density contrast that's here. Light stuff, heavy stuff. Heavy stuff recycled back down, light stuff stays on the surface. The light stuff doesn't just erupt out of these volcanoes, that's its origin, but also look how resistant it is. It stays up here, it doesn't subduct down. That's what the dense basaltic crust does, the dense oceanic crust. Right, so when you have a collision zone, it's the dense stuff that goes down where the lighter stuff stays up all the time. Okay, even in a mountain range or like a continent-to-continent collision, like between India and Asia, that's making a big mountain range, the Himalayan mountain range. It's not making a subduction zone. Neither one of those things is buckling to go down to the mantle. It's too light. It's too buoyant. They stay up there on the surface. Okay, so they are resistant to subduction. Now, this is where we're going to pick up next then, is this idea of some of the Earth's crust being resistant to subduction. Okay, but in the meantime, today's dose of violence, of violent volcanism, is sadly, or is brought to you, but a sad tribute here. David Johnston, that died in the Mount St. Helens eruption. He was a volcanologist, 1949 to 1980. Here's a picture of him taken a couple of days before the eruption. He was also doing some surveying up near the top of Mount St. Helens. Here he is going into the crater of Mount St. Helens. Before the big eruptive crater, this is the small volcanic crater that was there before. And David Johnston was so dedicated to his science of volcanology, this sect of geology, that he took it upon himself to make all of these measurements, everything that he possibly could to understand this sequence of the events leading up to the eruption. And sadly, he didn't evacuate, he didn't leave, and died in the eruption. Okay, so that is our daily dose of violence today. A little bit of quiescent crust and making the Earth's crust, oceanic crust, and placement of granites, making continental crust, a little bit of violent volcanism, and we'll stop there and pick back up, and well, me, happens to be in a couple of minutes, for a larger global tectonic reference frame. Okay, here we are, back again, a little bit more violence. So, today in Violent Earth, after the quiescent crust and after developing the crust of the Earth, the silicate insulating layer on the outside, via granite emplacement and violent volcanism. Whew, I've had a little bit more coffee now. I'm a little bit more jolty. Now I want to get into this, back out once again into the global tectonic reference frame. Okay, global tectonic reference frame. So I want to talk about this idea of cratons of the Earth, and it's really easy to get stuck in the weeds on this one, so I'm going to try to give an overview without getting too detailed and too intense here, as you know can happen. But really, I just want to give you the idea here of a craton, and then we'll talk about exotic terrains, or effectively how the crust of the Earth. In the last lecture, we talked about thickening through time, but it's exotic terrains that actually builds crust wider through time, okay? And then I want to talk about, something called the Wilson cycle. And this is J. Chuzo Wilson in a Pokemon card, if you're familiar with that game. All right, kind of an older slide here, but this is just a nice tribute to slow down for a second in Violent Earth. And what we have not done in this class yet is address life. We've mostly been dwelling on geology and a lot of this background of violence, but really this word violence, even in that context of immense powerful forces of nature, it's subjective from life, from living things, I think. So we are headed towards the impact of violent events on living things on Earth. And so I just want to give this sort of token of appreciation to Rob Hunter and the Grateful Dead about us here living on Earth as the eyes of the world. This is one of my favorite songs and favorite lines of this. Sometimes we live no particular way but our own. And then we wake up to find out that you and I are the eyes of this world, are the eyes of this planet. Okay? I think that has, it's a cool song, but it also has an immense kind of philosophical undertone about us in the space age right now, today, with the ability to use telescopes, binoculars, naked eyes, and to look out at the cosmos. And over this time that geologically we like to call the Anthropocene, humans, right, the whole Homo sapiens kind, have really become the eyes of this planet that are looking outwards to the cosmos. Okay, we'll come back to that at the very last 2 lectures of Violent Earth, where we talk about our violent relationships with this planet. All right, back up a second. We had gone over this diagram at length quite a few times to build the crust via light chemicals floating and heat escaping. And it was through the light compositions remaining on the surface in an ever-increasing amount that we talked about the continental and oceanic crust thickening through time. Now, continental crust, as you saw in one of those last diagrams, doesn't subduct, but oceanic crust does. So oceanic crust doesn't really get thicker through time. Okay, if it has gotten any thicker from the Archean style of plate tectonics, it still subducts, it's still dense, and it still recycles back into the planet. But what gets left over in the ever-increasing amount is the granitic crust, or the continental crust of the Earth. So that's where the ideas of cratons is going to come from, is these remain on the surface of the planet in an ever-increasing amount. So you can imagine then, we started off with wee little bitty tiny little bits of this stuff, and then, increasing through time, we are getting more and more and more, ever-increasing amount of this felsic-rich crust on the surface. Okay, and that, then, is what we can call a craton. So here's that same series or sequence of diagrams that we had gone through with the creation of oceanic crust before the ophiolite sequence, and to show that what was being created in the Proterozoic time period, or the Proterozoic time, is much more like continental crust, with all these granite type of things that are in here. Now, I want to take you to a picture here of North America. I'm like a North American geologist. It's where I feel most comfortable doing geology. I've really never been off of this continent to go look at other rocks, right? I've been everywhere from Alaska to Mexico looking at rocks, but never overseas. So this is the context that I have. I'll use North America a lot for examples then, right? Here in North America, what we call the craton is the area up here, partially the Canadian Shield, which is exposed craton, or the exposed metamorphic rocks that make up the core of this planet, or sorry, the core of this continent. Okay, then it's the shield, and they're exposed because of the Pleistocene glaciation that had scoured all of this stuff. Now, areas to the south, and also here over in the kind of in the east of the Canadian Rockies, this area, which we call the platform, are ancient sedimentary rocks, about 500 million years old and younger, that covered up the craton. So the craton is still under here. You can drill beneath these sedimentary rocks, the package of Paleozoic rocks, and you can get to the craton that's here. Even down here in Oklahoma, there are the rocks of the Ouachita Mountains are billions of years old of parts of the craton. So my point here is the craton is like this. It's a very large chunk of rock. Some of it is exposed. You can go put your hands on it over here in northern Wisconsin. And some of it is covered up by younger sedimentary rocks, but it's still there. Now that craton is the undeformed core of North America, and by undeformed is it hasn't really undergone mountain building, major faulting, volcanism in the last billion years. Well, maybe once in the last billion years. There was one episode where the craton was starting to pull apart right here, and that actually made what's called the mid-continental rift, where it started to pull apart right here, and that's part of how Lake Superior got there. That's Lake Superior's origin story, but that was a failed rift. So it deformed a little bit, but then it got smashed back together by the Grenville orogeny and a mountain building event that was building a supercontinent. Okay? Now, before I get too far ahead of myself, I just want to slow down and point out North America has an undeformed core of rock that's for about 1 billion years, hasn't undergone any major tectonic volcanic events. Now, on the periphery, it has. On the periphery, there's all sorts of violent interactions that are happening there. Okay? And that's what we're going to look at, is how this craton has started out from this size about 1 billion years ago and has gotten bigger since then, right? Okay, until we have a larger continent today. Now, continent doesn't necessarily mean craton. Every continent does have a core to it of undeformed, much older, usually metamorphic rocks, okay, that would be considered the craton. Okay, a craton, to define that, a stable crust that is cold, so low heat flow, it's strong, and it is not easily internally deformed, and it has a low geothermal gradient, so it's not letting much heat out. Okay, what the heck is this picture? I want to just make the analogy really quick to think about these cratons. Remember that the light materials of the Earth are floating towards the surface to make up the felsic crust on the surface. So I kind of like the analogy of these being like little islands of bubbles or little bubble mats, okay, with floating on top of the water. Now, they're not like that exactly at all, right? This is just a simple analogy that's going to help for the next concept called accreted terrains or accreted exotic terrains. So if we have these little island bubble mats out here, these are like little cratons. And those cratons, as they're drifting across and they run into each other, they accrete together to make larger little piles of bubbles then, right? Okay, you have a little island of bubble over here, and it smashes together with the other bubbles, and it makes a larger soapy bubble pile, okay? Now, just pretend that the bubbles aren't going to pop, okay? Just leave that part alone. Point here is that the suds are coalescing together to make these larger accreted bubble rafts, okay? Now, keep that in the back of your mind. This is just an analogy to think about light materials coalescing together, okay? Now, this image was shown back when we were talking about Alfred Wegener and the continental drift hypothesis. And remember, the continents aren't drifting across the basaltic rocks at all, but instead, the oceans are rifting and are opening up from the middle and separating like this, okay? So that's part of what's driving this plate tectonic process. So this Pangaea, which was once this one large supercontinent, has rifted apart, started right here at what is now a mid-ocean rib, but a continental rift that rifted this thing apart, and then an ocean flooded into this. Now we have the Atlantic Ocean. Now, that was kind of a two-step process there that I wanted to show you there, right? You start out with, boom, supercontinent. Everything's kind of together, Pan, all, Gaia, together, or Earth, all together, and then it rifts apart. And we have this kind of modern day setting where there's maybe a couple little islands that are sitting out here, but not a whole lot, not compared to the Pacific, maybe more so down here in the Greater and Lesser Antilles. Okay, so that's a two-step process. You have supercontinent and then rifting apart, okay? Now I want to look at a little bit closer at some of these processes. Remember, this is the process as seafloor spreading, and I want to take a step back. So here's that supercontinent. Here's it rifted apart, but there's a mountain range here. Remember, Alfred Wegener looked at that and he said, hey, I think the Appalachian mountain range and the Chalcedonian mountain range, they might be connected if that was a supercontinent, right? And in fact, through rock evidence, he was able to show things of that nature, right? Like that. Now, why is there a mountain range in the middle of Pangaea, in the middle of the supercontinent, right? So then we kind of have to rewind and go backwards. What the heck, right? Why were there mountains there? How do mountains form? Okay, so if we look at modern day analogies then, and this example has come up a number of times, India And the Himalayan plateau in Asia, this is a convergent boundary where two continental land masses are converging together, making the Himalayan mountain range. So, why is there a mountain range here? Well, maybe these two were colliding together, continent to continent collision, making these mountains. Okay, so now we've added a pre-step 1 process then, right? So to make the supercontinent, you have collision, and then you have supercontinent, step 2, well, formerly step 1, and then you have upwelling of the mantle where these things drift apart as seafloor spreading. Okay, whoa. All right, let's back up, slow down a second, right? This is getting really crazy. And let's look at this through a couple of, a series of cross sections and look at this a little bit more closely on the east coast right here and look at some of the belts of rocks of the Appalachian Mountains. So you had supercontinent Pangaea. Okay, this is now taking that the map here of Pangaea and looking at that sideways, so we're looking at a cross section of the Earth. This is also not to scale, and this is just meant to kind of schematically show some of this stuff. But you have Pangaea that's rifting apart then, right, to make the Atlantic margin here. And these are what are known as graben blocks or fault blocks that are kind of like a bookcase. As you release the pressure from one side of the bookcase, the book kind of slumped down. And this is a really common geologic province that's seen in these areas of rifting or extending apart. Okay. Now before that, right, as we pointed out, and again that image here of Pangaea, there's a big old mountain range in the middle of it. So if we then go to a cross section of what a mountain range looks like in a continent-to-continent collision, this is what was happening before Pangaea was ripped apart. Okay, before the rifting occurred, first this colliding must have occurred, continent-to-continent collision. Neither one of those things is light enough to buckle under the other one to create subduction, right? So instead, these things are buckling together, making thicker crust, but also buoyantly, isostatically rebounding upwards, making very high mountains. And in one case, this is like the Himalayan mountain range. In another case, this is like the Rocky Mountains that are not too far away from us, right? Now it's a different, more young scenario, but similarly, continent-to-continent collisions cause really large orogens or orogenies, mountain-building processes. So mountain building via this process of by continental crust collision is called orogeny, the process of mountain building. Okay, in modern day, actually let me go back right here, you can see all these folds of these rocks as thrust faults are allowing this rock to thicken, right? Because this doesn't just happen like a pile of sand or something like this, right? Is that this has to happen through geologic mechanisms where the surface of the Earth is relatively brittle. And that happens through cracking and crushing, earthquakes. And those earthquakes happen along faults. And those faults, in this case, are faults that are thickening the crust, and one is pushing over the other one in the thrust fault. And that makes what are called fault propagation folds and leads to these vast areas called fold and thrust belts, like in southwestern Montana today. If we look at the east coast of North America, this is the valley in Ridge and Valley province of, I think of Pennsylvania, a portion of this. And here you can actually see all this fold. This is from the top. This is high topography in green, low topography. And what's outlined here, all those folds that we were seeing in the last diagram, except turned sideways, right? So we're actually seeing the axes of these folds just like a crinkled up rug. So the Appalachian Mountains do have record of that mountain building event, right? The Appalachians that were there. Okay, and in fact, if you look at the geologic makeup of the Appalachian provinces, here's the Atlantic coastal plain, the Virginias, Georgia, there's different belts of rock, just like that folded up belt of rock, that was one of the belts. Okay, but also periphery to that, there's all of these separate named belts of rocks as geologists were out there walking around with their maps and their rock hammers and looking at all this stuff and finding out that this rock belt is completely different from this rock belt. You can walk along this belt and everything's the same, but if you walk across it, you go into a different geologic province. And these things became known as terrains, not terrain like hilly terrain, but terrain with an A-N-E, T-E-R-R-A-N-E, a geologic terrain. And then later, at some point, these rocks became known as exotic terrains, because these rocks are very different than the rocks that are exposed next door to them. And it appeared that these things were exotic to that location. That these rocks, being so different from those rocks, they must have come from completely different areas. Another way to think of that was a allocthenous terrain, or, well, let's not invoke that word. They're from far away, exotic terrains, okay? So here's a couple of these different geologic maps from the East Coast that are showing these distinct packages of rock that are unrelated to the adjacent package of rock, right? Here's some Precambrian Devonian rock here in green that are unrelated to these Carboniferous rocks separated through time, for one, but also just very different package than that that's on the other side of this. Okay, so terrains are these distinct packages of rock. Terrain, terrain, terrain. Now, what does this have to do then with Pangea and going back to plate tectonics? So plate tectonics, remember, this was first a hypothesis, continental drift, that was built up by all this observational map evidence that, remember, was destroyed and it was thrown out of the geologic literature and marginalized until more observational evidence of the seafloor supported that hypothesis, and more data that have been collected since then have emblazoned this hypothesis to now call it a theory. So what I'm doing here is I'm kind of stepping back into all of these observations that help us look at the larger picture of plate tectonics. Okay, so here's one of these that was really important for the East Coast tectonics. The observation of noticing multiple terrains of the East Coast. So here's that physiographic image we were looking at a minute ago, which, remember, this physiography came from this earlier imprinted geology underlying this of all these folds here in these rocks, which after this is eroded down, the folds are exposed as something like this. Now, how did that happen? What must have happened then is a collision of continental material and continental material, okay? So here's this continent colliding with this continent. The future Valley and Ridge province, right here, this Valley and Ridge province here, the fold and thrust belt occurring out here in the leading edge of this orogeny, what's known as the Alleghenian orogeny. Orogeny, remember, mountain building. So this was a mountain building event that made up the Alleghenian province of the Appalachian Mountains. Now, I don't want to get too far into the weeds of words then, right? Okay. To do that, to have the Alleghenian orogeny, look at these different belts of rocks that are identified here. Okay, that rock is a terrain that's distinctively different from this rock. That's a terrain that's differently than this rock, Okay, so to do that, something like this must have occurred, right? To have this block of rock, this continent, move across an ocean or oceanic crust to collide with this one, you first have to have oceanic crust that's undergoing some sort of subduction, okay? And then as this plate subducts further and further and further, right? These are getting closer and closer and closer until eventually the collision forms. So continent-to-continent collision isn't the start of things. That's the end of a subduction process where the continents finally converge. It starts out as probably oceanic to continental, or even oceanic to oceanic, and the continents slowly get closer together and then finally collide. So to do this Alleghenian orogeny, first there had to be this, a subduction zone, erasing or consuming all that oceanic crust, and before that, the Acadian orogeny, where this package of rock is getting smashed onto the rest of these rocks. Okay, to do that, the Acadian orogeny, where Africa over here, the continent is getting closer and closer to North America, there must have been, to get this package of rock here, a subduction zone, making these granite andesitic type of volcanic arc rocks in a subduction flux melting type of situation before they could have been stitched on to the sides of those rocks. Okay, now we're going through the same process here. You see what's happening is we're unpeeling the Appalachian geology. We're taking apart those belts of terrains to figure out, geologically, where did they come from? How did those form, right? There's signatures there that suggest that that one was a volcanic island arc. There's signatures there that suggest that one was a continental volcanic arc. Okay? There's signatures in the rocks that are showing this. And this is all the reversing of all of that geology, the tectonic orogeny. And to do before the tectonic orogeny, there must have been, a margin of volcanic island arc out here to create those rocks that later collided. Okay, so I think you're getting the picture here of the East Coast didn't look like it does today before Pangea formed, right? It was something completely different, but as Africa was coming in to collide and form Pangea to make those mountains, there were multiple islands that were in the way that collided and collided and collided and grew the North American craton outward in this direction. It grew wider before Africa smashed in to make Pangea, right? Which then, of course, later rifted away. And here's evidence of yet an older rift. Because remember, we just peeled away all the Appalachians before Africa even got there. What is there a rift there for, right? These rocks are actually still preserved on the west side of the Appalachians as a Paleozoic passive margin. Okay? So we have a rift margin that looks very similar to one of these oceanic rift margins that started out as a continental margin, right? Half of a continental rift. All right, so let's look at this in words for a second. What did we just go through? It's kind of like a cycle then, right? It starts out with continent, supercontinent. It rifts apart where ocean basins form between it. Then subduction initiates on one side or the other. And then that subduction consumes the oceanic crust, which leads those continents further and further and further together, maybe consuming little islands, little terrains on the way. And then they collide to make another supercontinent, forming mountains. And then slowly, those mountains, after the collision slows down, gravitationally collapse, causing more rifting. Continental rift, ocean basin opens, subduction initiates, ocean basin closes. It's a cycle, okay? This is what's called the supercontinent cycle, or also known as the Wilson cycle, named after J. Tuzo Wilson, a Canadian geophysicist that first coined this idea. That maybe, just maybe, Alfred Wegener, with his old Pangea idea, right? The thing that he identified, this all Earth together, maybe that wasn't the only one. Maybe this is like an accordion process, right? That there's multiple of these supercontinents that form here. Rifting, ocean basin forms, they come together, collide, supercontinent, rift. Okay? So that was an idea, right, a hypothesis that came out of, right, this idea of terrains, the observation, of multiple terrains, that to build the Appalachians and the Chalcedonies, to build portions of the east coast of North America, there had to have been a collision before Pangaea rifted, or before, there had to be a collision of some sort to rift, there had to be a rift before Pangaea could have formed together. And that rift is showing that there was a previous supercontinent before that. Stumbled there. Okay, so let's look then at some of what we know today of this evidence. There are at least 4 very well known, lots of geologic data behind each of these, known supercontinents, and then others are also speculated, and I'm not going to give much evidence for that. And I think that the names between and Kennerland, this is a little rocky. I'm still a little confused in the literature myself about some of these things, but the older that these things get, of course, by tectonics, that stuff is getting recycled down into the mantle, or the process of collision is burying stuff. We have fewer and fewer older rocks that are exposed. So we have less and less data to show that what these ones were up to. Okay? But there are at least 4 well-known supercontinents. Pangaea, you all know this one. Rodinia, before, which we had barely touched on when we were looking at Snowball Earth. Remember, Rodinia, the supercontinent, was spreading apart, allowing these basins to form where some of these glacial diamictites were deposited into. Okay? So Rodinia is actually key to understanding the Snowball Earth hypothesis. Rodinia. Before that, Columbia, about 1.6 billion years ago, and Kennerland, older than that, an Archean age supercontinent. Maybe the first and the oldest supercontinent that's like the rest, that's made of granite cores. Remember, this Archean time period, there's TTGs, little bits of granite that are floating around. So if there is a supercontinent, it's just tiny little bits of granite that are colliding together, little bits of bubble mats, right? All begins with a craton or several cratons that accumulate exotic terrains on the edges, on the margins, as these orogenic mountain belts. Okay? Let's take a look at some of these. So Nuna, Kennerland, again, I'll just restate that I'm a little confused in the literature. Looking, you go back too far, the name's a little bit different, the time frame. So I'm not a Precambrian geologist. We'll just kind of say that there's this older one, 2 to 2.5 billion years ago, with no comprehensive configuration, a collection of some of Earth's oldest continental crust, some of those old blobs of granite that formed by differentiation processes at early subduction zones, maybe. Okay? And this is the argument of when did plate tectonics start? Some would say that evidence of this supercontinent shows us that plate tectonics modern plate tectonics was well to do by then. Okay, so here's the age in Proterozoic time. Then the supercontinent Columbia, this is one of the possible reconfigurations of that. And here's kind of the outline of some of today's continents that are drawn around here. So here's North America, Greenland, Siberia, Baltica, Australia, India, right? You can see some of the shapes that are in here, South America. So we have some loose configuration of how each of these related to one another during the supercontinent Columbia. Now, what I want to point out here, here's Greenland and here's North America. Basically the same configuration that they are today with respect to one another. And that's very important, maybe not overall to the story, but kind of to us as North American dwellers, right, that we have a craton that seems to have been basically assembled, at least with these things, since the supercontinent Columbia, back there in the Proterozoic time period. Now, younger in the Neo-Proterozoic, we have the supercontinent Rodinia. And there's a lot that's known about Rodinia, right? This is only one accordion pushed back. So there's quite a bit of geologic evidence for the supercontinent Rodinia, mostly in the collisions that occurred that are recorded really well in both metamorphic rocks as well as the sedimentary basins that formed at the margins of those. So a lot of well-known research into the supercontinent Rodinia. Some of the major arguments are, was it Australia that was stitched onto North America, or was it Baltica that was stitched onto North America? And there's a lot of argument there, and I think both sides have a lot of interesting evidence. I'll stay out of that one. Okay, so supercontinent Rodinia about 1 billion years ago, and then of course, as we all know and love, the supercontinent that's on the foremost of everybody's mind, and probably up until about a half an hour ago, maybe the only supercontinent that you knew of, Pangaea, or all of Earth's continents together, but not for the first time, as you know now. So here we have the supercontinent Pangaea. There's a really good program out there, the Plates program. You can go visit their website and you can kind of go forward and backward through time up to today to kind of reconfigure Pangaea from the best of what we know of all these relationships. One of the coolest things I would say is to watch over the last, must be about the last 25 million years, to see India race across the Indian Ocean and to ram into Asia. It's really, really cool imagery. But anyway, Pangaea also is known to have kind of a northern half and a southern half. Laurasia, or this is for Laurentia and Asia stitched together, and then Gondwana, or South America, Africa, India, Australia, and Antarctica all kind of stitched together over here. And Gondwana, I want to point out, there's a popular political movement to reunite Gondwana land. We must stitch these continents back together into their original unoppressed form. Okay, now this is kind of a joke, but reunite Gondwana land. If you ever see that bumper sticker like on my car or other people's car around, you know what that means now, right? Is that it's kind of poking fun at just like big political statements on we better do this, where sometimes those things can be as impossible as closing the Atlantic Ocean and reuniting these continents. Okay, now I want to take a little bit of a tangent, as I'm always good for, to speculate a little bit about what happens next. Okay, now we're not in the business of prediction here, but if we keep looking at the geologic context, then there are some things that we can see geologically that are occurring over the next X millions of years. Now, first of all, I want to point out my speculation about this first. That there's, if we look at a map of the age of the oceanic crust worldwide, I realize this map shows up really small on the video screen, so making sure you're looking at the lecture slides posted online. In this map, you can see the red colors are really young oceanic crust, 0 millions of years old. The purples and the blues, the cooler colors, are the oldest oceanic crust that's out there on the surface of the Earth, at 270 million years old. It's not very old as far as overall. Remember, we have billions of years old rocks into the cratons. Remember, the cratons are growing thicker and wider through time, where the oceanic crust just keeps getting subducted and recycled. So it's quite young. Remember, the process is opening and closing, opening and closing, opening. How does it close? Subduction begins on one side, right? Subduction begins on one side to close the margin. If we look at the oceanic crust, where is the oldest oceanic crust that's becoming old and cold and dense and sinking into the mantle to form a subduction zone? Up here on the eastern margin of Canada, Nova Scotia, right? And then over here near the Straits of Gibraltar and outside of Portugal. It is one of these two areas then, I would argue, are very susceptible to this old cold crust forming a subduction zone to then close up the Atlantic margin, just like we have today. And in fact, it was only a couple years after I had kind of speculated this for myself, maybe the first time I had ever said it to a class, There's a paper, oh, it's right here, the subduction zones invading the Atlantic, evidence from the southwest Iberian margin. Right here, there's actually been some imaging of the ocean floor showing that there are thrust faults on the bottom to suggest that there is subduction that's initiating, and these sediments are little thrust faults on top of that. So we do have some evidence of subduction beginning here. Interesting. Okay, so look forward in the next 25 million years to the Atlantic Ocean closing and having another supercontinent. Now, before we get that far, I also want to point out it's well known in some of these supercontinents like Rodinia and Columbia that mantle plumes, which I've only invoked in name thus far, we'll pick it up again later, mantle plumes that cause supervolcanoes are also known to break up supercontinents. As they're coming up from the core mantle boundary and they hit the lithosphere and they cause this buoyant rise, that can cause the buoyant rise to split, right? Just like the splitting of a balloon as it bursts or something like this. That plume can cause it to split and the continents to drift apart from one another. Okay, it is speculated that there's a super plume underneath of Africa today that's causing this bulging, and maybe the African subcontinent is going to be rifting away, just like Madagascar has already done, or the East African Rift Valley is starting to. And right in my backyard, right over here to the east, at the end of the Snake River Plain, is the Yellowstone hotspot, Yellowstone National Park, here at the Star. And if we go back and look at the geology of when the Columbian supercontinent was stitching together, okay, the Columbian supercontinent was made of these older Archean pieces of crust, parts of or Kinnerland or Nuna, that collided together, part of the Superior Craton, the Wyoming Craton, Medicine Hat and Hearn Craton, that collected together. Now remember, between the cratons as they're colliding, this collision zone, it's mountainous, right? Or this is an area where the rocks are being bashed and faulted together. So they're all weak. It's a weakly faulted zone. That zone then is an area of weakness that as the mantle plume that's stationary, as the North American Craton drifts on top of that mantle plume, I suggest that that area of weakness is a great area for the mantle plume to break apart this craton. So here's that weak belt of rock running through the Dakotas. Here's the Yellowstone hotspot. North America's moving in this direction, right? A couple million years from now, the Yellowstone hotspot hits the Thor boundary, or the Trans-Hudson origin boundary, and rips these things apart. And we can say, bye-bye East Coast, right? No, I'm just kind of joking there. But so this is speculation, right? This is not in geologic literature at all. This is really just, crazy guy standing up here. Instead of looking at information and literature that's published, this is a hypothesis, right? Is this a testable hypothesis? Not really, forward in time. What we can do is we can look back at comparisons of how mantle plumes interact with these weak boundaries. If there are none, there are none, right? All we can do then is speculate about this and not have a testable hypothesis. Okay, now people have thought about this. This is not published in any peer-reviewed material as far as I know. This is there are multiple maps that are put out there, but people have thought about the Atlantic margin closing up and to create a future world, or what's also known as Pangea Ultima, where Pangea is re-stitched together as the Atlantic margin closes apart. Okay, this was made in 2000, years before the paper that I just showed you, the Iberian margin subduction zones. So I think the geometry here that this person has is definitely off, right? They're supposing that subduction would start somewhere else, and that Africa would run into North America, rather than Eurasia, or the Iberian Peninsula, running back into North America. All right? Anyway, today's dose of violence, all about accreting terrains and mountain collisions and orogenies, and then of course the supercontinent cycle of making multiple supercontinents through time. Though it might not sound all that violent, probably was, right, at different punctuated times with supervolcanoes in between. Brought to you today by Canadian geophysicist J. Tuzo Wilson, and a nice Pokemon player card with his great move, Prove. J.T. Wilson used Prove to show Alfred Wegener's theory was right. Okay, and that's the end of Violent Earth sequence today, going all the way from Earth's quiescent crust to global tectonics. Next week, we will pick up on some major violence, some asteroid impacts, extraterrestrial bolide impacts that have changed the face of the Earth through time. And it's a shorter lecture in order to save and preserve some of that new information time for studying for the week 5 exam. Okay? Have a violent Earth. Peace out.